So next, we will look at the reflective property of a hyperbola. And there are two versions of this property, which is fitting since a hyperbola has two branches. The internal reflection property states that a ray from one focus of a hyperbola is reflected by the hyperbola in such a way that it appears to have come from the second focus. The external reflection property states that a ray directed towards one focus of a hyperbola is reflected by the hyperbola in the direction of the second focus. So let's look at these properties in action. The internal reflection property is that a ray that originates from the first focus is reflected by the hyperbola in such a way that it appears to have come from the second focus. And in the external reflection property, a ray that is directed towards the first focus is reflected in the direction of the second focus. So notice that the triangle P, F1, F2, which includes the point T on the transverse axis in the external property, is the same as the triangle P, F1, F2, which again includes the point T on the transverse axis in the internal case. And so the corresponding angles with respect to the tangent line are the same. And so we will prove the internal reflection property of a hyperbola by showing that the angle that the incident ray makes with respect to the tangent is the same as the angle that the reflected ray makes with respect to the tangent. Okay, so let's sketch a hyperbola. And we will choose to position our hyperbola in the standard position so that the center occurs at the origin, and the coordinates of the first focus is a times e0, and the coordinates of the second focus is negative a times e0. So when a ray originates from the first focus, it is reflected at the point P on the hyperbola, and that point P has coordinates a secant t, b tangent t, and it is reflected at that point in such a way that the reflected ray appears to have originated from the second focus. And we also need to look at the tangent line through the point P. That tangent line intersects the x-axis at the point T. Now we need to show that the angle that the ray from the first focus to the point T makes with respect to the angle, or rather with respect to the tangent line, which is the angle alpha, is the same as the angle that the reflected ray from the point P makes with respect to the tangent, which we'll call beta. Now notice that here we have a vertical, vertical angles, and so angle TPF2 is also the angle beta. And so we want to show that alpha is equal to beta. And so as with the ellipse, we're ultimately going to use the law of sines, and so we need to establish some ratios of lengths for the two triangles. So we're going to need to know the coordinates of the point T. So recall that the tangent line for through a point P on a hyperbola is given by secant t divided by a times x minus tangent t divided by b times y is equal to 1. And so when the tangent line intersects the x-axis, y is 0. And so we have secant t divided by a times x is equal to 1, or x is equal to a divided by the secant of t. And so the point T has the coordinates a divided by the secant of t, 0. So let's now look at the distance from the point P to each of the foci. The distance from P to the first focus is e times the distance from the point P to the directrix corresponding to the first focus, which is the directrix with the equation x equals a divided by e. So this is e times a secant t minus a over e, which is a times e secant t minus a, or a times the quantity e secant t minus 1. So let's now look at the distance from P to the second focus. That is equal to e times the distance from the point P to the second directrix corresponding to the second focus, which is the directrix with the equation x equals negative a divided by e. So we have e times a secant t minus a negative, or so plus a divided by e. So that's a times e secant t plus a, or a times the quantity e secant t plus 1. And so the ratio pf1 to pf2 is e secant t minus 1 over e secant t plus 1. So let me recreate the triangle. So angle TPF1 is alpha and angle TPF2 is beta. So we want to determine the distance from T to F1. And so that is the x-coordinate at F1, which is a times e, minus the x-coordinate at the point T, which is a divided by secant t. And so we have a times e secant t minus a all over secant t, which is a times the quantity e secant t minus 1 all over secant t. And the distance from T to the second focus is a over secant t minus the x-coordinate at the second focus, which is negative a times e. So we have minus the negative or plus a times e. And so we have a plus a times e secant t all divided by secant t, or a times the quantity e secant t plus 1 divided by the secant of t. And so the ratio TF1 to TF2 is e times the secant of t minus 1 over e times the secant of t plus 1. And recall that that is the same ratio as PF1 to PF2. And so the ratio, we can rearrange this ratio so that we have PF1 to TF1 is the same as PF2 to TF2, so that we can apply the law of sines. So sine of the angle alpha to the side TF1 is the same as sine of the angle PTF1 to the side PF1. And so the ratio PF1 to TF1 is sine of the angle PTF1 to sine alpha. So next, the sine of beta, the ratio of the sine of beta to TF2 is the same as the sine ratio of the sine of the angle PTF2 to the side PF2. And so the ratio PF2 to TF2 is sine of the angle PTF2 to sine of beta. Now notice that the angles PTF1 and PTF2 share a common vertex on the horizontal line. And so those are supplementary angles. So since angle PTF1 plus angle PTF2 is equal to pi, we have that angle PTF1 is equal to pi minus the angle PTF2. And so the sine of the angle PTF1 is the sine of pi minus the angle PTF2, which is the same as sine of the angle PTF2. And so since sine of the angle PTF1 to sine alpha is equal to the ratio sine of the angle PTF2 to sine beta, and the numerators are equal, we have that sine alpha is equal to sine beta. And since alpha and beta are both acute angles, we can conclude that alpha is equal to beta as required. So next, let's look at the reflective properties of a parabola. So the reflective property of a parabola is that a ray parallel to the parabola's axis of symmetry is reflected by the parabola in the direction of the focus. Or, conversely, a ray from the focus of the parabola is reflected by the parabola in the direction parallel to the parabola's axis of symmetry. So let's see this property in action. An incident ray that is parallel to the parabola's axis of symmetry is reflected by the parabola in the direction of the focus, or conversely, an incident ray originating from the focus is reflected by the parabola in the direction parallel to the parabola's axis of symmetry. So notice that the tangent line through the point P, the reflection point, intersects the parabola's axis of symmetry at the point T. So let's sketch a parabola. And we'll choose the parabola to be in the standard position with its vertex at the origin. And so the focus occurs at the point A0. Now an incident ray that is parallel to the parabola's axis of symmetry will be reflected at the point P, and that point has coordinates at squared 2at. It'll be reflected at that point in the direction of the focus, and the tangent line through the point P intersects the x-axis at the point T. And so we'll need to know the coordinates to the point T. So recall that the tangent line through a point on a parabola is given by 2at times y is equal to 2 times a times the quantity x plus at squared. And so when the tangent line intersects the x-axis, y is equal to 0, and so we have x plus at squared is equal to 0, or x is equal to negative at squared. And so the point T has coordinates negative at squared 0. Now let's focus on the triangle TFP. Now the angle, let's have our incident ray on the dotted line. Now the angle that the ray from the point P to the focus F makes with respect to the tangent, let's call that alpha. And the angle that the reflected ray, or correction, the incident ray makes with respect to the tangent, let's call beta. Now, since we have a vertical angle, this angle here is also beta. And since we have two parallel lines cut by the transversal TP, then this angle, which is PTF, and the angle beta are alternate interior angles. And so the angle PTF is the angle beta. And so by the law of sines, we have that sine of alpha over TF is equal to sine of beta over PF. So the distance from P to F is the same as the distance from P to the directrix with the equation x equals negative a. And so this is the x-coordinate of the point P, which is at squared, minus a negative a. So this is a times the quantity t squared plus 1. Now the distance from the point T to the point F is the x-coordinate of the focus, which is a, minus the x-coordinate of the point T, which is negative at squared. And so we have a minus a negative, or a plus at squared. So this is a times the quantity 1 plus t squared, which is a times the quantity t squared plus 1. So we have that TF is equal to PF, and hence sine of alpha is equal to the sine of beta. And since alpha and beta are both acute angles, we can conclude that alpha is equal to beta as required.